one. So the capabilities are actually, yes, an over-approximation of all the accesses that will happen. Then the authorities of the capabilities are a subset of the most pessimistic approximation that we can do. That is, just look at the tree of all the capabilities present in the language. And then two important properties, 3 and 4, that we'll go back on later. So I'll give you practical examples of them. One essentially says that only connectivity begets connectivity. That is, in order to access a new resource, you either have a pointer to it or you receive a pointer from somebody else. And then that there is no authority amplification. That is, you cannot grant yourself permission to access resources that you didn't have permission to access in the first place. That authority must come from somewhere else. In the literature of capabilities, there are lots of other interesting properties, but we focus only on these ones because these are the ones that are really needed for isolation. So let's see the dynamics of authority. As I said, it depends on the execution of the state. So we have Alice, and we represent in the blue shaded area of the graph its capabilities, its authority. And after the execution of Alice, we'll have a new heap graph, so a new set of resources containing each other, and we change some arcs there. And what we want to know is what happens to the authority of Bob while Alice has exercised her authority. Okay, so that's the problem we're going to look at right now. Now, if we have a system that is capability safe, according to the definition I gave, then it will respect the only connectivity begets connectivity condition. And therefore, that condition says that if initially the authorities of Alice and Bob are separate, after an execution of Alice, no matter what she's able to do, the authorities will remain separate. And in particular, from that follows that the authority of Bob after the execution of Alice will be exactly the same as the one that it had before, because of this disjointness property. It's a very strong property. The other property was the no authority amplification. So in this case, instead, we don't have disjoint authorities. We cannot use the connectivity begets connectivity. We have instead that the purple node there is a resource over which both Alice and Bob have authorities. Now, after the execution of Alice, the authority of Bob this time has changed, but we can put a bound on how it changes. Okay. So if a system is capability safe, then at most the authority of Bob can be its initial authority plus the initial authority of Alice, all in a block, plus whatever new authority Alice may have created. But that excludes Bob essentially having new authority by magic. The only new authority that may come is because of the execution of Alice, and we know it by that intersection over there that we had to look in all the authority maps of Alice and see if anything new came up. At that point, we know a bound on the authority of Bob. It's not the whole system. Whatever was unreachable even by Alice remains unreachable. Note in particular also in the diagram that Alice's authority has increased in this case just by creating new nodes. So it can create new resources and of course therefore inherit an authority over those new resources, but is not able by itself to gain access to that white node that didn't have access to in the first place. In order to do so, she will need to receive the authority to do that from another party. So we have these two properties, and they help us relate the authority of Bob before and after a transition by Alice. And so we use this to generalize and to isolate these components. Okay, so the condition that we request on a system in order to satisfy authority isolation is that for each initial heap, the various components for each two different indexes, they should not have overlapping authority. If we are able to prove that, where again the notion of authority is dynamic and it requires a rather sophisticated analysis in order to be bounded, then we have a theorem. And the theorem says, okay, as long as you satisfy this definition in your system, then you will know that all the accesses to any resources in the language during the execution of any of the components will be independent component-wise. Therefore, you have complete intercomponent isolation, okay, which excludes the case of components collaborating, but captures the case of not tampering with each other's state. This proof is, again, based on the generic model of the programming language, so it can be adapted but to other cases, but is, in particular is true for JavaScript. We have a very precise model of JavaScript. We model the whole specification of the semantics according to the ECMA 262 committee, and so it's a pretty faithful reconstruction. You can pretty much rely on this result. And now, how do we generalize this notion? So what we found that is in this isolation theorem, improving it, all we rely on are these two properties, connectivity, big S connectivity, and no authority amplification. So that's what we have to focus on. We can just define a notion of authority safety instead of capability safety that is actually focused on these three properties, these two properties, plus the initial one. And so in this way, you have to do less work in order to prove that your system is isolated. So now we look for something that is weaker than capability safety. But of course, capability safety is still useful. So if you have a capability language in itself, is a weaker property, is a stronger property, you know how to build an authority such that this three property holds. So we are very happy if we have a language like Kaha or a language like Joey that, or Emily that are already capability safe because we know authority safety holds. But it's authority safety itself that gives you the isolation property, so the mashup isolation. Therefore, you can also build mashups in something that is not an object capability language, just proving those three properties at the top. And that is actually much less work than building a whole framework like Kaha. So part of the complexity and of the penalty performance of Kaha is to do with making it a real object capability language. As far as isolation is concerned, you need less. You need authority safety. You can do less work. And now I'm going to show you an example also that differentiates. So, as I mentioned, the idea is you want to isolate mashup. Okay, if I know one of those two properties, I know I get isolation. What I need to prove is also that I have the proper enforcement mechanisms that support a language being either capability safe or authority safe. So that will require some effort. It's actually the core of the effort, because once you've done that, by the theorem, you get isolation for free. So we applied this approach to JavaScript, unfettered in the sense of, let's just take JavaScript, not an object capability language. Let's show that a subset of it is authority safe, the most interesting subset we can find. And then at that point, we know we can do isolated mashups with that. And that's a language that we call a JSafe. It's a subset of JavaScript that enjoys authority isolation. And then we said, okay, now let's take an object capability subset of JavaScript, the Kahita subset, which is part of the Kaha framework by Google. And we formalized the core of Kahita, and we proved that that one is capability safe. So in principle, is a harder proof to do, but the language that we're looking at is not just wild JavaScript. It's very well behaved. It's already capability safe. We just have to show that it is. And so in that respect, it's an easier task. But of course, the distance between, let's say, Kahita and JSafe, the other language I just talked about, is the complexity that then is paid in terms of other measures in the Kaha system. Okay, so now I focus a bit on the JSafe part of the story. So this pure JavaScript subset, we needed to define a reasonable notion of authority map so that it will be authority safe. And in order to do so, also we need to put some enforcement mechanisms in the language that will restrict it so that one cannot do very nasty things and access the global object wherever you want and start doing object prototype poisoning and other typical JavaScript nastities. So we started with some subset of JavaScript we already had. That was the one that I mentioned that enforces host isolation. And that's all based on the idea of filtering out something that is too dangerous, like eval, then rewriting something that is too general, like the bracket notation. So we don't want to let you get the global object and then access the string eval, otherwise our filtering of eval would be pointless. And then, in particular, we do that by rewriting it and then wrapping some native functions, because some of those native functions can be used in an improper way to access parts of the language that we were trying to protect anyway by this eval and by that rewriting mechanism. So we combine these two techniques, we isolate the host. Then we separate, now we have many components, each one is isolated from the host. We have to isolate them from each other. We can separate their namespaces, essentially is a simple technique. All the global variables are prefixed by a component-specific identifier, plus a bit of bookkeeping, but that's the intuition. And that almost works. But there are still problems with the shared functions of the language. So in particular, if you redefine, if you not redefine, but if you add to the toString method of a random object that is in your own object space an attribute, we call channel, then whatever you put in this channel can be retrieved by another component just by going again to the predefined toString method and reading that attribute that he didn't put there. But what actually happened is that that attribute was saved somewhere in the shared space of the JavaScript environment. So we need to stop that. Or you can even misuse other functions, like the push and pop properties of arrays. You can take them off the array, just run them as a top-level function, and that will push and pop a piece of data just on the global object. So that's a way that without you using global variable or without you creating new properties of objects, you're just passing data from two components. Okay, so you break this isolation. We need to stop all these mechanisms. What we do is we have to make native functions and objects read-only and wrap the native functions so that they cannot take their these cannot be instantiated to the global object. Okay, so in the host isolation problem, our wrapping was to avoid a native function to return the global object, and instead to isolate components, we must avoid a native function to receive the global object, essentially. So the pop of an array must be run on an array and not on the global object. So this resulting subset is called JSafe. So we have defined the authority map for it. We have shown that it's safe in a safe authority map. So we have authority isolation. And by the theorem, that implies full isolation for the mashup programs. So based on this formal result, we have compared the language with Facebook, FPJS, and with Yahoo.Safe. And we actually found discrepancies. Now, when there is a discrepancy, what's going wrong? Either the two things can coexist, or one of the two has a problem in it. And it turned out actually that we found real attacks both in Facebook and in Yahoo. So in their isolation mechanisms, there were actual flaws. They were fully exploitable vulnerabilities that would give you the whole browser, essentially. And so talking with them, then we convinced them to fix them and to remove them from the system. But if you want to see the details, then you'll have to get to the paper and look inside. It's a paper that was published at Oakland 2010. So concluding, we have formalized the notion of capability safety that already existed, and we thought it was useful for mashups. Yes, it was useful to isolate mashups, but there is actually something that is a bit simpler, that is authority safety, that is actually the core of what you need. But of course, this authority safety being weaker, it means there's less property. In particular, for example, it doesn't guarantee absolute encapsulation or defensive consistencies, other very nice properties of object capability languages. So what we plan to do now is to push more that part of the work and include them into our formalization. And we believe that we can, in a similar way, then establish a weaker form of isolation between components so that a component can share code, as is the goal of the Google Kaha framework, not be isolated vertically, but they can call each other's function and not have their own state disrupted. So that's the goal of this research in the future.